methods used to change the magnetic flux linked with the coil. We have already discussed that the magnetic flux can be changed by changing the magnetic field, by changing the area of the loop in the magnetic field. Now we discuss the third method, that is by changing the orientation of the coil in magnetic field. Now say this blue color is a coil and this one is a magnetic field. Magnetic field is perpendicular to the plane of the loop. That is, the magnetic field is in the direction of the area vector. Now the flux linked with this loop is equal to B dot A. The initial flux, as the angle is 0, so we can say that the initial flux is BA. Now as this loop rotates, the angle between the magnetic field and the normal to the loop changes. So the final flux is BA cos theta. Now see, it is rotated, so the angle between the normal and the magnetic field changes. Now say it is theta. So flux is equal to NBA cos theta. If there is only one turn, we use the relation BA cos theta. If there are n turns, we are using the relation NBA cos theta. Now theta is equal to omega t. Put the value of theta. The equation becomes NBA cos omega t. As you know, EMF is equal to minus d phi by dt. So we differentiate it to get the EMF. So when we differentiate this cos omega t, then its differentiation is minus omega sine omega t. Minus minus becomes plus, so it becomes NBA omega sine omega t. Okay. This can be written as E naught sine omega t, where E naught is equal to NBA omega. Now the question, a closed loop is held stationary in the magnetic field. Loop is stationary in a magnetic field between the north and south pole of two permanent magnets held fixed. Can we hope to generate current? As the loop is stationary, it means no change in the area of the loop. Magnets are fixed, no change in the magnetic field. Current will be produced if the loop rotates, so that the angle between the normal to the loop and the magnetic field changes. Only in that case flux changes and the EMF can be induced. But here, can we hope to generate current in the loop by using the strong magnets? If in place of these weak magnets we are using the strong magnets and that are also fixed, and there is no change in the orientation, then no EMF is produced. Now second part of the same question. The closed loop moves normal to the constant electric field between the plates of the capacitor. Is current induced in the loop? No, no current is induced, because the current will be induced when either the magnetic field or the area of the loop or the orientation of the loop changes. But here there is no magnetic field, so no EMF is induced. Whatever be the condition, whether it is wholly inside or whether it is partially, no EMF is induced. Now the third part. A rectangular loop and a circular loop are moving out of the uniform magnetic field region to a field-free region with a constant velocity. Both are moving with the same velocity. In which loop do you expect the induced EMF to be constant? Till this position, no EMF is produced as they are in the magnetic field and there is no change in the flux. When it is taken out from this area, then it is expected, it is hoped that in this case, in a rectangular case, the EMF is constant. In the circular case, the rate of change of area with time is not constant. So, it is expected that induced EMF is constant in a rectangular loop, as rate of change of area is not constant in the case of circular loop. Now the next question, the metallic rod of 1 meter length is rotated with a frequency of 50 revolutions per second. So omega equals to 2 pi n. With one end hinged at the center and the other end at the circumference of a circular metallic ring of radius 1 meter. About an axis passing through the center and perpendicular to the plane of the ring. So it is a rod which is rotated. It is connected with the ring and is rotated. Here the magnetic field is in inward direction. Rod is moving in perpendicular to the direction of the magnetic field. So according to the Fleming's left hand rule, the force is acting on the electrons and the electrons get separated. They move towards the ring. And due to the separation of the charges, the EMF is induced. And after some time, the magnitude of the EMF is constant. Now we have to find out the magnitude of this EMF. Let suppose DE EMF is induced in the DR part of this ring. Okay? DE is produced in the DR part of this rod. As you know, EMF is equal to minus BL V. So here in place of L, we use DR. For a small portion, it is minus B V DR. For the full rod, it is integration of DE, integration of BV DR for the complete length of the rod. In place of V, use R omega. So this will be the expression. Now put the value of B omega R square and answer is this one. So main is this formula. It is a one method. The alternate method to get this formula is as it is hinged, here the linear velocity is 0 and at this point the linear velocity is v. So the average velocity is 0 plus v by 2. Using the formula of motional EMF BLV. In place of v, we are using the average velocity. So it becomes BLV by 2. Now v is equal to L omega, same relation. So it becomes L square omega by 2. Here L is R, so it is B R square omega by 2. So the same formula either by this method or by this method.